Hello again. Today we're going to be talking about Riemann sums, which is a way to approximate the area under a given curve. So let's get started. If I do want to approximate that area under a curve, like the one on the right, what I can do is I can create some rectangles that cover approximately the same area as the curve itself. So what I've done is I've written down some x's, x1, x2, x3 along the x-axis, and I can use those. The width of the rectangles can be given by the distance between each pair of x's. So between 0 and x1, I can call that delta x1. From x1 to x2, I can call that delta x2, and so on. I can call each of those distances delta x sub I. And that value can change between every pair of x's. Now the height of each rectangle is going to be given by a y value, a function value for some x inside each of those intervals, so I call that x sub I as well. Now sometimes I may want to use the leftmost x of every interval, and that will give me the red rectangles there. Sometimes I might want to use the rightmost x in every interval, and that will give me the green rectangles. And sometimes, if I think it's better, I might want to use the x that's in the middle, the exact middle of every interval. And so I call that a midpoint approximation, or a midpoint Riemann sum of rectangles. Now, if rectangles don't give me a good enough approximation, what I can do is I can use trapezoids instead. That could get me closer to the actual area, but it still does leave some gaps and some overages. It's still an approximation of the area under the curve. To calculate a trapezoidal sum, if you've already calculated your left rectangle Riemann sum and your right Riemann sum, you can just average those together, and that will give you the area of trapezoids. All right, so the left-hand Riemann sum is going to actually always underestimate the area of any increasing function, because as you see, those rectangles are always going to be underneath the curve. Now if we're talking about a decreasing function, now the rectangles are all above the curve, and that will give you an overestimate of the actual area under the curve. And quite the opposite, right-hand Riemann sums are going to overestimate the area of increasing functions, and they're going to underestimate the area of decreasing functions for the same type of reason. Now when it comes to midpoint Riemann sums, we're not really looking at increasing or decreasing anymore. We're looking at whether the function is concave up or concave down. So a midpoint Riemann sum is going to underestimate the area of a concave up function, and it's going to overestimate the area of a concave down function. And then the opposite of that would be your trapezoidal sums, which overestimate the area of concave up functions and underestimate the area of concave down functions. So here's a summary right here in this table. So a left-hand Riemann sum is going to overestimate when a function is decreasing. It's going to underestimate when a function is increasing. The opposite is going to be a right-hand Riemann sum, which is going to overestimate when the function is increasing and underestimate when the function is decreasing. The midpoint sum is going to overestimate when the function is concave down and underestimate when the function is concave up. And then the trapezoidal sum is going to overestimate when the function is concave up and underestimate when the function is concave down. So the best way to do this is to look at an example. So there's a table right here, and I don't really know what the graph looks like. All I have is some points, x and y, that are on the curve somewhere. Okay, so my prompt is, using three rectangles of equal width, estimate the area under the curve using a left Riemann sum first of all. So the fact that I'm using rectangles of equal width is important because the x's go from 1 to 7, which is a width of 6. And so if I want the rectangles to have equal width, then they all have to have a width of 2. So the first rectangle is going to go from x equals 1 to x equals 3 because that has a width of 2. The second rectangle is going to go from x equals 3 to x equals 5, and the third one is going to go from x equals 5 to x equals 7. All of those have a width of 2. Now to figure out the heights of those rectangles, because I'm using a left-hand Riemann sum, I'm going to be looking at the y values that are on the left-hand side of each of those intervals. So the y value for x equals 1, for x equals 3, and x equals 5. So those are my heights. The widths of the rectangles are all 2. So if I do 2 times each of those y values and add it all up, then I get 18.8. Now this is an underestimate because, as you remember, if the function is increasing, the left-hand Riemann sum is always going to provide an underestimate of the area under the curve. If I'm doing a right-hand Riemann sum instead, I'm not going to be looking at the y values for the x's on the left side of the interval. I'm looking for the y values of the x's that are on the right-hand side of each interval. So I'm looking at the y value for x equals 3, x equals 5, and x equals 7. So that gives me y values 3.0, 5.1, and 8.0. So if I multiply each of those by a width of 2, add it all up, I get 32.2. Now this is an overestimate because, again, the function is increasing. The y values keep going up. Now I'm going to do a midpoint Riemann sum, and it's important that I do have the y values for the x's that are exactly in the middle of each interval, otherwise I really can't do a midpoint Riemann sum. Luckily I do. I have the y value for x equals 2, 4, and 6, so I can actually do a midpoint Riemann sum. I multiply each of those y values by 2, add it all up, and I get 23.2. So maybe that's a better estimate of the actual area under the curve. And the last one is a trapezoidal Riemann sum, and remember, to do that I'm just finding the average of the areas of the left-hand Riemann sum and the right-hand Riemann sum, and if I do that I get 25.5. That's going to give me my area of the trapezoidal sum, and so since I really don't know the concavity of f, I really can't say whether the midpoint Riemann sum and the trapezoidal Riemann sum are overestimates or underestimates. So it's not really fair to ask that question. So that is pretty much an example of how to find each of those Riemann sums. If you have any questions on this, please let me know, and I will see you tomorrow.